Hello everyone. In yesterday's presentation, we saw the design procedure of a center crankshaft. As we all know that a crankshaft can be of two types. One is center crankshaft and other is side or overhung crankshaft. In today's presentation, we will discuss design of a side or overhung crankshaft. So at the end of this presentation, students shall be able to understand the design of side crankshaft of an IC engine, which includes design of crank pin, design of crank web, design of bearings, basically their length and diameter, and design of shaft under flywheel. We have seen in yesterday's presentation also that the difference between a center crankshaft and a side crankshaft is that in a side crankshaft there is only one crank web and there are only two bearings, whereas in a center crankshaft there are two crank webs and three bearings. So the complexity is a bit lower as compared to a center crankshaft. It is used in medium size engines and large size horizontal engines. As you can see that these are the two bearings. This is flywheel where with the help of belt power is being transmitted, and this is crank web and this is crank pin. So our job will be to find the dimensions of crank pin, basically its length and diameter, the dimensions of crank web, basically its width and thickness, the dimensions of bearing, that means their length and diameter of shaft uh, on which this flywheel is being mounted. Similar to the center crankshaft, in a side crankshaft also, there can be two cases. Case 1, when crank is at top dead center position, and case 2, when crank is at an angle with line of dead center producing maximum torque. So we will be discussing these two cases in detail for a side crankshaft. Let us first discuss the design procedure of a side crankshaft when it is at top dead center position. You can see in this diagram that there is only one force acting vertically downwards, which is denoted by this PP, that is force on piston, and there are this vertical load which is due to the weight of flywheel, and this is horizontal load which is due to the belt tensions. Since there are only two bearings, the reactions on bearing has to be calculated. The reactions due to this PP load are denoted by R1V, whereas reactions due to this W load are denoted by R1-V and R2-V. Similarly, reactions due to this P1 plus P2 load are denoted by R1-H and R2-H. So we'll first find the reactions, all the reactions at the bearing 1 and bearing 2, and then we'll proceed for finding the diameter and length of crank pin and dimensions of crank web and other dimensions. Let us first find the bearing reactions. For the sake of simplicity, the force diagram has been drawn, linear force diagram has been drawn, just to make a bit simple that which force is acting at what distance. Now, force on piston is simple, pi by 4 d square into p max. Our job is to find the reactions, vertical as well as horizontal, on bearing 1 and 2. With the basic understanding of shaft design and finding moments about the bearings, we can find these reactions in vertical plane as well as horizontal plane. For example, if we consider this force PP and ignoring W over here, we can find reactions R1V and R2V. Let us see how. This B is the length from bearing 1 to the line of action of force PP, and C is the distance between bearing 1 and bearing 2. So if we take moment about bearing 2, what will we get? This force PP into distance B plus C, that is PP into B plus C, equals to this vertical force R1V, which is reaction at bearing 1 due to vertical force, into this distance C. So R1V will be PP into B plus C over C. Similarly, if we take moment about bearing 1, we'll be able to find what is R2V. So R1V and R2V are the reactions due to the vertical load PP. Similarly, W is also vertical load due to weight of flywheel. So reactions due to this are denoted by R1-V and R2-V. We can find that this is from this diagram. Similarly, in horizontal loading, there is single load which is equal to P1 plus P2. So we need to find R1-H and R2-H from these basic formulas. So till now what we have done, we have found reactions on both the bearings in vertical plane and in horizontal plane, considering the three forces, that is piston force PP, weight of flywheel W, and sum of belt tensions in the horizontal directions. If we found this, the rest of the job will be much easier. How? Let us see. After finding the reactions, our next job will be to find the dimensions of crank pin. We should consider this line as a line which is denoting crank web, means it must be having some thickness and some width. So first of all, we'll need to find the dimensions of crank pin. At bearing 1, we can find this bearing pressure which is equal to PP over LC into DC. LC into DC is the projected area and PP is the force. So force over projected area is bearing pressure. This L and D ratio is generally 0.6 to 1.4 and bearing pressure is 10 to 12 megapascal. So if we see this equation again, we have converted L into D using this ratio. We already know PP and PV is in the range of 10 to 12 megapascal. So only unknown left over here is DC, that is diameter of crank pin. And since we have assumed the L by D ratio, length can also be determined. So with this simple analysis, we have found what is length and diameter of crank pin. But we have taken only assumptions like L by D ratio and bearing pressure. We also needs to check it from the stress point of view. So what we'll do, we'll assume that crank pin act as a cantilever. This is acting as a cantilever with load PP over here. Now this PP load can be either assumed uniformly distributed. If it is the case, then maximum moment will be PP into LC by 2. If load is assumed to act at the end of crank pin over here, then the maximum bending moment will be PP into LC. The actual case will be somewhere in between of these two cases. It was LC by 2, it is LC. So taking mean of it, we can assume that load PP is acting at 3 by 4 of the length. The mean of half and 1 is 3 by 4. So MB will be 0.75 pp into LC, or we can say in other words that MB is pp, which is load, into length, which is 0.75 LC. In all the future analysis, we will assume the load pp to act at a distance of 0.75 LC. So MB is known to us because we know what is LC. So we'll find sigma B by 32 MB over pi dc cube. From this equation, we already found what is LC and what is DC. So we'll be in a position to find what is sigma B. This sigma B should be less than or equal to sigma permissible. So what we have done in this slide, we have just found LC and DC by bearing pressure considerations, and then we have duly checked it for stresses. If in case this sigma B comes out to be more than sigma permissible, in that case we need to change the dimensions of LC and DC. Proceeding further, let us talk about the dimensions of bearing 1 and bearing 2. Obviously, these bearings will be identical bearings. So let us do the analysis. Bending moment at bearing 1 is given by this equation. How? Let us see. Assuming that this point is in the mid of the bearing 1. So bending moment will be PP into 0.75 LC, which is this distance, plus this line is being shown for the thickness of crank web. So plus T plus distance 0.5 of L1. L1 is length of bearing 1. Since it is assumed that 0.1, this 1 is at the center of the bearing. So distance from the center of the bearing to load PP will be given by this equation. Now there are empirical relations for L1. L1 is taken as 1.5 DC to 2 DC. There is also empirical relation for thickness T, which is thickness of web, that is 0.45 DC to 0.75 DC. So we can check it for the stresses induced. How? Putting these values, we will find MB, and for the bearing we already know what is your section modulus, so we can find stresses for the bearing material and it should be within permissible limits. Further, we can also check it from the bearing pressure point of view. Bearing pressure at bearing 1 is R1. R1 is resultant reaction at bearing 1, which is nothing but R1V plus R1-V upon L1 into D1. We have taken L1 and D1 from these empirical formulas. R1 is already known to us. We can find PP from here. If the PP is within 10 to 12 megapascal, the values that we have assumed for L1 and D1 are okay. Next, we need to find the dimensions of crank web. In fact, we have already taken dimensions W and T as some empirical relation. Now we need to check for the same. The crank web is subjected to eccentric load PP. Here it is crank web and here it is load PP. Now stresses will be developed one is direct compressive and other is bending stresses. How? Let us assume that this is the crank web. So to know the effect of this PP force on this crank web, what we'll do at the CG of this crank web, we'll put equal and opposite forces equal to PP. So this downwards force PP will create compressive stress, and the couple which is being formed by this PP vertically downwards and this PP vertically upwards will create bending stress. So that compressive stress will be given by PP over area, which is W into T. We can assume W as 1.14 times DC. Thickness of web we have already found from the empirical relation in the previous slide. So we can find what is sigma DC, which is direct compressive stress. Now the next stress is bending stress. So bending stress will be PP plus distance this, which is to up to the crank web, it is total is B, or we can say 0.75 LC plus T by 2. We need to find bending at the midpoint of crank web. So this is MB, bending moment at the central plane, and section modulus, since the section is rectangular, it will be 1 by 6 WT square. So we'll find sigma B. Now net stress will be, since both are normal in nature, net compressive stress is sigma DC plus sigma B. It should be within sigma permissible. If it is the case, then the thickness and width that we have assumed are okay. If it is not, we can increase the width, because increasing width will not affect other calculations. Coming to the next uh, component, that is design of shaft under flywheel. This is the shaft where flywheel is being mounted. We need to find the diameter of the shaft. So central plane of the shaft under the flywheel is subjected to maximum bending moment. Now it will be subject to maximum bending moment due to the forces, which is PP, and due to the forces due to the reactions, which is vertically upwards here. So we'll find MBV by this formula and MBH, bending moment in the vertical plane and bending moment in the horizontal plane. We know MBV, we know MBH, so we can find what is resultant bending moment. This formula will give us resultant bending moment. I for the shaft is pi ds 4 upon 64, where ds is the diameter of flywheel shaft and y is ds by 2. If we know the stress for the shaft material using this equation, the only unknown left is ds. So we can find what would be the shaft diameter under flywheel. So this was the cases that we have discussed till now pertains to the position of crank at top dead center. There can be one more case when crank is at an angle of maximum torque, means it is producing maximum torque. Similar to the analysis that we have undertaken for center crankshaft, here also we will be having three forces now: tension force PT, radial force PR, and the resultant PQ. And this, the condition of maximum torque occurs at a angle theta of 25 degree to 40 degree. So with the simple force analysis, we can find value of PQ, value of PT, which is tangential component, and value of PR. So now the state of forces will be a bit complex as compared to the case when there is only one force PP. Remaining forces, that is weight of flywheel and belt tensions, will be same. This is the line diagram of forces which will act on bearing 1 and 2 and on the crank pin. This PR force and PT force, which is component of force PQ, and this W force vertical downwards, and this P1 plus P2, this is belt tensions in the horizontal direction. The assumptions are the engine is assumed vertical, belt drive is assumed horizontal, and crankshaft is simply supported on bearing 1 and 2. So again we need to find reactions on bearing 1 and 2 considering the changed scenario of forces. Earlier we used to have only one force PP over here, but now we are having PR as well as PT. So on bearing 1, earlier we used to have only the vertical reactions. Now there will also be horizontal reactions. So this is the loading in vertical plane. We found what is R1V, what is R2V, what is R1 dash V, and what is R2 dash V. The difference over here, I'll repeat once again, that this R1V and R2V are due to the tangential and radial components, and this R1 dash V and R2 dash V are due to the weight of flywheel W. Similarly, this is the line diagram for horizontal loading. So again, we'll find R1H and R2H due to tangential component PT, and R1-H and R2-H due to this P1 plus P2. Now, since we have found what are the reactions at bearing 1 and 2 due to the changed state of loading, our next job is to find the design of crank pin. In fact, we have already found what is length and diameter of crank pin. So what we'll do, we'll just check whether with the calculated value of diameter and length of crank pin that we have done when the crank is at TDC, top dead center position, with the same values, we'll try to find the stresses induced. If the stresses induced are within the permissible limits, our calculated value is okay as far as the stresses in the crank pin are concerned. So, since we have taken that, we'll assume the load to be acting at a distance of 0.75 LC from crank web. We found what is MBV, what is MBH, that is bending moment at in the vertical plane and bending moment in the horizontal plane. We'll find resultant of these two. Z, which is section modulus of pi dc of the crank pin, that is pi dc cube 132. Since everything is known to us, we'll find the stress. This stress ought to be less than or equal to sigma permissible. Now we'll need to check the design of crank web also for this crank at angle of maximum torque. The crank web is subjected to the stresses. One is bending stress in horizontal plane and vertical plane due to radial component PR and PT. Then direct compressive stress due to radial component PR. There is additional stress, torsion shear stress due to this tangential component. So we have got two normal stresses and one shear stress. What we'll do, we'll find bending moment due to radial component at the mid section of the crank web using this formula, and we'll find sigma BR since we know what is LC and what is T. Then we'll find bending moment due to tangential component from this formula. We know PT and we know R. R is crank radius and D1 is diameter of shaft at the juncture, which is this. So we'll find sigma BT from here. So sigma BR, sigma BT. Next is direct compressive stress, which is PR over area. So since they are all same in nature, we'll add them algebraically to find resultant sigma C, compressive stress, sigma BR plus sigma BT plus sigma CD. Next is torsional moment. Torsional moment is given by PT, 0.75 LC plus 0.5 of T. We are finding it at the midsection of crank web. And Z, polar section modulus for a rectangular web is given by WT square O 4.5. It is worth mentioning that we know every dimension over here, that is width of web, T, thickness of web. So we just need to check whether the stresses induced are within permissible limits or not. Since we have got normal stresses as well as shear stresses, we'll use the normal stress theory and we'll find sigma C max. It should be less than or equal to sigma C permissible. If it is not, that is, if sigma c max is more than sigma c permissible, we can increase width of web as it does not affect other calculations. Then we'll find the diameter of shaft under flywheel. In fact, we have already found that. We need to check. So the central plane of shaft is related to bending moment in the horizontal and vertical plane and torsion moment due to tensile component PT. Using this force diagram, you can easily find what is MBV and what is MBH. So we'll find the resultant of these, and then torsion moment will be PT into R. So resultant shear stress for the flywheel shaft material tau is this. We already know ds from the case 1 analysis. So we'll find the stress induced. It should be less than equal to tau permissible. So what we have done till now, we have analyzed the case of side or overhung crankshaft for two cases. Case 1, when the crankshaft is at TDC, and case 2, when the crankshaft is at an angle of maximum torque. So you might see that in both the cases, it is possible to find dimensions like crank pin, width and thickness of crank web, diameter of shaft under flywheel, bearing dimensions, etc. Now there can be two strategies. First strategy is we'll find dimensions for both the cases, case 1 as well as case 2, and the dimension which is coming out to be more for a particular element will assume the dimension as the final dimension. That means if the dimension of crank pin is coming out to be more for case 2 as compared to case 1, we'll assume the dimension for case 2 as final. Similar is true for other dimensions. There can be one more scenario in which we'll find dimensions for either case 1 or case 2, and then we'll check for the induced stresses for the other case. That means if we have found dimensions using case 1, then we should check the dimensions for case 2 by checking for the stresses induced. They should be within the permissible limits. If they are within the permissible limits, our design is safe, and if they are not within the permissible limits, we should modify the dimensions. I would here, and I would like to mention one thing, that side crankshaft is basically a shaft. So if we have the basic understanding of how to find movements, how to find reactions, what will be the effect of particular bending moment or particular force at a component, we can easily find what would be the nature of stresses induced. So the analysis may look complex, but in actual it is not that complex. It is very simple. So I request all of you to please go through the same. One more thing I would like to add, that ample help will be provided to us while solving questions on crankshaft by means of design data book. So we should not be panic that how we'll remember all these analysis. Our job is to just lay down a framework using which we can design crankshaft. It can be center crankshaft, it can be side crankshaft. So I hope you have enjoyed the presentation. I request you to undergo the presentation a couple of times so that you will be familiar. And as always, for better understanding, we'll solve some numericals also. I thank you all for your patient hearing.